All right, let's do 4.1 probability distribution. All right, let's look at a little vocabulary. We've got a random variable x represents a value associated with each outcome of a probability experiment. Give me a few minutes and I'll show you what that means. The random is that x is determined by chance, and then we're going to have two kinds of random variables, discrete and continuous. So discrete means that there's a finite or a countable number of possible outcomes. So let's say we were looking at how many TVs a family has. They might have 0 TVs, they might have 1 TV, they might have 5 TVs, but those are countable and they're what we call finite. You can't have infinite number of TVs. Continuous is different. We can't count them because we actually have lots of fractions and decimals. So this would be maybe how much rain fell, right? Because we could have 1.5 inches, we could have 1.25 inches, we could have 1.2 inches. We couldn't count them because there's so many different decimals and fractions on the number line. I'll show you an example. Right, for discrete random variables, so this is an example of that. If you conduct a study of the number of calls a telemarketing firm makes in one day, so they could make 0 calls, 1 call, 2 call, 3 calls, they could make a ton of calls, but they can't make half a call. They can't make quarter of a call. And then the day is up. They can't make infinite number of calls because they only have 24 hours. So there's no fractions, no decimals. There is a stop to the number of calls because when you move over to the next day, you start counting again. So those are called discrete random variables. Now, if we were looking at the time spent making calls between 0 and 24 hours, I get it that the 24 hours would be over. However, we could have a call that took 1 hour and 2 minutes, 1 hour and 5 minutes, 1 hour and 50 minutes, 12 hours and 1 minute. And so because we can use all of the number line and all of the decimals and fractions in between, we are going to say that this is a continuous random variable. So if you're using just the tick marks on the number line, that's going to be discrete. If you can use all of the fractions and decimals, then it's going to be continuous. All right, let's take a look here. We have let X represent the number of Fortune 500 companies that lost money in the previous year. So the number of companies, you can't have half a company, you can't have a quarter of a company. You could have 0 companies, you could have 1, 2, 3, and then you can't have more than 500, right? You can't go on to infinity. So we are going to say that that is discrete. And then we have the volume of gasoline in a 21-gallon tank. So even though it's a defined 21-gallon, we can have fractions of a gallon, and therefore it's going to be continuous because we could have all kinds of different fractions between the 0 and 21 gallons. Okay, let's look a little more. Let X represent the speed of a rocket. Okay, well, again, speed can, it would be continuous because you could have miles per minute, miles per hour. I don't know how they would represent the speed of a rocket, but we could have fractions of that. Let X represent the number of calves born on a farm in 1 year. Well, you can't have half a calf. So this is going to be discrete, and it stops after 1 year and you start counting again. So that would be discrete. Now the next one is a little tricky. It says, let X represent the number of days of rain, not how much rain. How much rain would be continuous because you'd have fractions of inches. But the number of days, you would only have 0 days, 1 day, 2 days, or 3 days. So that would be a discrete. So number of days of rain would be discrete. How much rain would be continuous. Right, these are very important. We're going to look at what's called a discrete probability distribution. When we do that, we're going to look at a table of data. We have to make sure that each probability is between 0 and 1 inclusive. So it can be 0, it can be 1, it can be any fraction or decimal in between. But a probability cannot be negative, and a probability cannot be greater than 1. So that's very important. And then also, all of those probabilities need to sum to 1. So just like when we were looking at complements and the probability of event E plus the probability of the complement is equal to 1, this is the same thing. We're just going to have more variables and more probabilities, but they would all need to sum to 1. Right. So if we were creating a discrete probability distribution, we would look at each of our discrete random variables. We would grab the frequencies for each of those variables. We would, of course, get the sum of the frequencies so that we could find the probability. We would take each frequency divided by the total. And then once we did that, we'd have to double check and make sure that none of the probabilities are less than 0 or greater than 1. And we would also have to make sure that they all sum to 1. Let's take a look at our frequency table here. An industrial psychologist administered a personality inventory test for passive-aggressive traits to 150 employees. Each individual was given a whole number score from 1 to 5. So that's our discrete score, where 1 is extremely passive and 5 is extremely aggressive. The score of 3 indicated neither trait. So we have 1, 2, 3, 4, and 5 for our scores. So those are discrete. The results are shown in the table below. And we want to create the probabilities. So what we're going to do is they did tell us the total was 150, but I went ahead and added them up here. So I added the frequency column. That gave me 150. Now I have to work my way down and find all of the probabilities. So first I'm going to take the frequency of 24 over 150. That gives me 0.16. Then I take the 33 over 150, 42 over 150, 30 over 150, and 21 over 150. We did these in chapter 2. So that gave me all of my probabilities. Now I have to look at those probabilities. Okay, so here's the same problem. I created a table here where I have X, the discrete variable, and I have the probabilities that we found on the last page. Okay. So I do need to double check and make sure that each of those is between 0 and 1 inclusive. Looks good. I have 0.16, 0.22, 0.28, 0.20, 0.14. So none of those are negative. None are greater than 1, so I'm good to go. I do need to double check and add them up and make sure that they sum to 1. Now, sometimes because of round off error, they'll be a little bit off. They might be 1.01. That's okay, as long as it's really close. That happens because of round off error. So if I add those probabilities all up down here in the bottom right, I get 1.00. So I am good to go. Now I can create my bar chart. So my variables across the bottom, 1, 2, 3, 4, and 5. I've got my tick marks here, my vertical my vertical axis. And so like number 1 is 0.16. So I'm going to come over here to 0.16 and draw my bar. 2 is 0.22. So I'm going to come up here to 0.22 and so on. All right, here's a different problem. The company tracks the number of sales new employees make each day during a 100-day probationary period. So the results here are sales per day. So I've got 0 through 7, nice discrete variable, and then the number of days. So that's my frequency. We would need to find the relative frequency. So what you're going to do is divide each frequency by the total. So you would add all these up. They would sum to 100 because there's 100 days. And then you would take 16 over 100 gives you the probability 0.16, 19 over 100, 0.19, and all the way down. Then you would have to pick a histogram. I have some instructions here on the bottom if you want to go ahead and put this into StatCrunch. But you should be able to see it in the homework. It's going to be multiple choice. And so you'll be able to see which bar chart works with your probabilities over here. All right, this problem gives me the days of rain, so discrete variables, 0, 1, 2, and 3, and then the probability for each. And they want me to go ahead and check and see if this is a probability distribution. The first thing we have to check is that each of these probabilities is between 0 and 1 inclusive. So it can be 0, can be 1, and we're good. There's no negative numbers. There's no numbers greater than 1. So that fits the first criteria. The next criteria, we need to add them all up. So you're going to take all 4 of the probabilities, add them up, and you need to get 1, right? So if you add up the probabilities, that needs to equal 1. And so that one's good too. So this distribution is a probability distribution. All right, let's look at the first table here. Our probabilities look okay. We've got 0.28, 0.21, 0.43, 0.15. So those are all between 0 and 1 inclusive. However, when I go to add them up, I get 1.07. That is a no-go. So this one is not a probability distribution. On the second one here, we have a big problem. Even though they would sum to 1, they do not fit our criteria. We cannot have a negative. We can't have a number greater than 1. So this one also is not a probability distribution. All right, one more example of looking at this criteria to see if it's a probability distribution. So my first table here, everything looks okay for being between 0 and 1. I have 1 over 16, 5 over 8, 1 over 4, and 1 over 16. So those are all between 0 and 1 inclusive. Use your calculator to add those up. Don't find common denominators. And if you add those 4 up, you get positive 1. So this one is good. Right, this one is a probability distribution. Now the second one, it fits the first criteria. All of the probabilities are between 0 and 1 inclusive, but when we go to add them up, they equal 1.04. That's not going to work. It has to be 1 or really close to 1. And so this is going to be no, it's not a probability distribution.